All right, welcome back, students. If you're joining this after taking a little break, as a refresher, the join code for Adam's lecture is 602987, and for Kevin it is 393390. And so this is the second grouping of lecture here with regard to satellite imagery and what we can glean from it. And so we left off talking about the electromagnetic spectrum and looking at, again, this black line showing the level of absorption, and then throughout that region of wavelength, the spectrum here of the wavelength, or even better term would be the range here in wavelength, we're looking at areas where there's high level of absorption, such as down here due to UV, here due to water vapor, and again here due to water vapor. And so different constituents in the atmosphere serve as absorbers within various portions of the spectrum. And so these next couple slides are a bit more on the complicated side. We'll go through these relatively quickly and don't get too stressed about them in many ways. And so what we're looking here is the areas where we have the bands within the GOES imagery sensor. And so here we're looking at channels 1 through 6. You can see in all of these there's a high response. We have some blues. We have some reds. This would be the one that we looked at in the last lecture here at around the 0.64 micron for the red imagery. Another one here around 1.35 microns, another one around 1.6 microns, another one here a little bit above 2.2 microns. And so in all of these we're looking for a pretty strong response with regards to what type of transmittance occurs with the atmosphere. We'll talk a little bit more about what we mean by that here as well on an upcoming slide. Looking more into the infrared portion of the spectrum, some of that was the near IR, but now we're looking now deeper into the IR portion of the spectrum. And so here you're looking at wavelengths that are getting longer and longer. And so here we're actually kind of working backwards. I'm not a huge fan of that, but it is what it is. And here we're looking at channel 7 down here in the lower right, around that 3.9 micron. Working our way towards things more related to water vapor imagery. We'll talk a little bit about some of these near the 6.7 micron later on, and then getting into the longer portion of the IR spectrum all the way out here to channel 16. And so what you have kind of hanging out here in the background is some information on brightness temperature, and then something with regard to the response that is being received by the satellite. And so let's get back to a couple slides that are going to be a little more pertinent to what you're expected to know moving forward in weather technology and for classes after this. And so here we're looking more at now the types of imagery. And we're going to start off with the visible wavelength. And here we're focusing on channel 2 around that 0.6 micron wavelength. And so visible imagery is one that you're used to. You've used visible imagery. You've seen it on the nighttime weather broadcast. And so here we're looking at what is effectively being reflected in terms of visible imagery back out to the satellite. And so we know what gets reflected is going to be much different if it hits something in the atmosphere such as water vapor or cloud droplets versus if it makes it all the way down to Earth's surface, because we know that as that visible imagery makes it down to Earth's surface, it gets absorbed by the Earth and re-emitted as infrared imagery. And so therefore you can see in this image, we can see a mid-latitude cyclone here somewhere over the southern United States. Nice comma head feature, and so we can see some bright white colors indicative of these clouds versus maybe areas here in Texas where it's really dark, where we're having very little cloud cover, and therefore we're getting not a lot of that visible imagery reflected back to the satellite. It's being transmitted through the atmosphere all the way down to the ground, and as that ground absorbs it, it does not reflect it back in the visible spectrum. Visible imagery is very helpful during the day. We can monitor a lot of really high resolution features, monitoring thunderstorms, tropical cyclones, mid-latitude cyclones, cirrus, all kinds of different things we can pick up relatively well here in this visible portion of our satellite imagery. And so again, we can tell the difference between hot ground, wet ground, blowing dust, fog. We'll talk a little bit more about different ways that we can delineate fog, as well as some other kind of more obscure things such as volcanic ash. But again, what's important here to recognize is that this is going to collect that light from the visible spectrum that's been reflected back to space. It's basically taking a picture, a photograph of the Earth. And so this is going to have really good spatial resolution. But as we've alluded to back in MET 103, the big downfall to visible imagery is, of course, the fact that if we don't have visible light, we're not going to be able to use this imagery, and so it's basically useless during the night. Here's an example of this true color type imagery, again merging some of the different wavelengths within the visible spectrum, and again produces a really nice image which we can enhance, showing where we have different layered clouds. You can almost kind of pick up where your deeper clouds are within this image. You can pick up some of the higher level cirrus that may be spilling on the back end of some type of a feature, mid-latitude cyclone. You can see here where you have some texture to the clouds, where there's a little bit lower of an angle, for instance. You can even potentially see down here in the Caribbean where we have some land sea breeze type setup trying to produce some thunderstorms during the daytime hours. We can use other things within the visible spectrum to pick up phenomena such as dust. So in this image you can see that we have some dust likely coming from the Sahara and moving over the Mediterranean Sea. In this image, this is from a number of years ago, but we can again look at this type of imagery to be able to pick up other particulates in the atmosphere that may not specifically be weather, but have a contribution to what's going on in our atmosphere. This is an older image, and it's to give you a little bit of appreciation not only for what this would have been very high-end imagery and effectively taken a very long time to download from the interwebs in 1997. Note the GOES here is 8, but you can still see a number of other features that are quite useful with regard to using visible imagery. And so what you have here across Wisconsin, northwest Illinois, Iowa, and into Nebraska is not clouds, but rather snow cover. And if you take a moment and look at it, you can probably pick out a number of interesting features. You can see, for instance, even though our state borders are showing it, the Mississippi River. A number of other river tributary type features here out in Iowa. Here we have the Platte River working its way through Nebraska. You can see aspects of the Missouri River. And again, where you would not necessarily have snow cover piled up over these rivers, you're going to be able to pick them out. So it's another way that we can kind of determine where the edges are of snow cover using satellite imagery. So again, here's a very interesting image from 2007 showing snow cover. Again, you can pick out many of the rivers throughout Illinois, Indiana, even in Ohio. But a couple other things that are really interesting here. You can see a smoothness to the clouds here stretching from Jersey down through the Delmarva into western Virginia. You can see that we have more snow cover potentially over New York. If you've never heard of the Finger Lakes region, you can see the Finger Lakes here. But you can also see these cloud streets that are forming over the Great Lakes. This instability from warmer lake water, cold flow over, and you can see a number of these features even here over Lake Michigan as this air flows from northwest to southeast. It takes a little bit of time, but eventually starts to form clouds and these banded type features. A really fascinating image that in today's day we would be able to pick out with much greater resolution. If we work our way into the long wave portion, infrared radiation imagery, here we're looking at channel 14, around 11.2 microns. And so, whereas visible imagery is not useful during the nighttime hours, long wave imagery is going to be able to be picked up because it is going to be sensing the temperature of objects. We usually call this IR. It is not infrared, as I might have thought as a young meteorology major. No comment. But beyond that, we're simply looking at infrared imagery. And this is going to be what is emitted. Again, key difference: reflected for the visible, emitted here in the IR channel. And so if we take ourselves way back to Met 103, we remember the Stefan-Boltzmann law. Stefan-Boltzmann law is going to state that the amount of IR radiation that's emitted by an object is proportional to its temperature. And so if you need to take a couple of moments and crack open your old Met 103 textbook, go for it. But the idea here is that warmer objects are going to emit a lot more energy. And so here we have cold cloud tops that are being signified by our enhancement as yellows and reds, showing these deeper, colder cloud tops, as opposed to these cool colors, which are actually indicative of some warmer surface temperatures. Mind you, this is in April 2019, so we probably have some pretty warm air here over western Texas and down in towards the Mexican plateau. Another strong mid-latitude cyclone at this point moving its way through the southeastern United States, and so where we have some of these more intense thunderstorms out ahead, probably along our warm frontal boundary, and then stretching down here over the Gulf in conjunction with some type of a cold frontal boundary, we can start to pick up where you're getting colder cloud tops and therefore less emission. And you can take a look here again at your scale and realize a little bit in terms of temperatures what is actually being emitted by these objects. Again, looking at IR imagery, this is from a number of years ago. Powerful winter storm here over the northeast. Band of deeper, colder cloud tops out ahead of your cyclone, wrapping in behind. Some warmer temperatures again here showing up over such areas as Florida. Other things that we can utilize within this portion of the spectrum here, the infrared, is differenced images. So if you look at the upper left here, you'll note that this is looking at the 11 micron image and comparing that, or differencing it I should say, with a 3.9 micron image. And what this is related to is the different emissivities of things such as water vapor, low clouds versus high clouds, so on and so forth, at different portions of the electromagnetic spectrum. And so you would use an image like this in conjunction with other products to be able to delineate a large expansive area of fog over Texas. You may also have some areas, for instance, over the Appalachians, down here towards southern California, and even potentially off the East Coast that are also experiencing fog with this. Another interesting tool when we can combine different channels within our satellite imagery. And so we'll talk here about water vapor, take another short break, and then we'll talk a little bit about actually analyzing jet streams, troughs, and ridges. And so now we're looking at that mid-level water vapor. This would be equated to channel 9 within our GO 16 imagery. And when we talk about water vapor, we're effectively looking at the response. What is being absorbed by water vapor in the mid to upper levels of the atmosphere? Water vapor is an extremely useful tool. I should say water vapor imagery is a very useful tool in identifying a lot of features, but it is also something that we need to take a bit of time so we understand what we're actually looking at. It's a common misconception that you're looking at how much moisture is, for instance, down near the surface. What is maybe our threat for severe weather? Do we have a high dew point? And that's actually not what we're looking at here. Here we're looking at things between approximately 650 and 350 millibars. Again, looking in the mid-levels to even into the upper levels of the atmosphere. The name water vapor suggests that the satellite is looking for regions of moisture. In fact, we're actually looking for regions where radiation may have been absorbed by moisture in the atmosphere. So again, to do a little comparison, back with visible, we're looking at reflected imagery. With infrared, we're looking at emitted energy, and now we're actually looking at the absorption of radiation by water vapor. And so we look in some of these. This would be a colorized enhancement here at 6.9 microns. We're going to look for the coloration of pixels. Is that radiation being absorbed, and therefore, or I should say, is the radiation being absorbed by the satellite, and therefore indicating a lack of moisture and dry air in the middle portion of the atmosphere? Is it bright, meaning that it was not absorbed by the satellite? It was caught by that moisture in the mid-levels of the atmosphere, or potentially that the ground is simply just not emitting a lot of radiation. And we can use these tools to effectively be able to pick out items such as jet streams, as I've alluded to a couple of times already. And so this is the example that I'll leave you with, and then we'll start up one last little bit shorter version of these slides. And here you can see where we look for bands around a cyclone. This is an older image, but you can see a nice flow over here off the Pacific coast, a deepening cyclone, and we see this dark band that's kind of stretching up into the middle portion of the country with ample moisture out ahead of it. And so this is going to be one way in which we can tell how cyclones are developing. Again, the idea that we take radio sound measurements twice daily, but we're getting regular higher temporal resolution of these this information within the satellite, and therefore we're able to monitor the development and the motion better than we would be able to with just observations alone. And so we'll take a break. We will come back with one last series of lectures and talk a little bit about troughs, ridges, and jet streams using this type of imagery.